Hello, welcome again to the course on Relativity and Cosmology. So after having discussed in detail the mathematics and also the general formalism of the Einstein equation and its properties, we now come to major applications. So the first is gravitational waves. And this is a very important topic because, as you perhaps have heard, 5 years ago, for the first time we were able to directly observe gravitational waves. And gravitational waves are solutions that propagate, or waves that propagate in empty space-time. So they are pure curvature in a sense. Now, gravitational waves, we know from electrodynamics, of course, what electromagnetic waves are. And in particular, we call them radiation solutions. Radiation behaves as follows, is characterized by the behavior of the field strengths, in this case the electromagnetic fields at infinity, so that they only decrease with 1 over r instead of 1 over r squared as you have for static fields. Then they are characterized by the existence of an energy flow, and also there is the connection of the radiation field with a source, so that you, for example, can talk about the energy loss in the antenna. Now, the antenna has energy loss and there is energy in the electromagnetic wave. Now for gravity, there are subtleties. It's a bit problematic because the concepts of field strength and energy are not as clearly defined as in electrodynamics, and because of the equivalence principle we can transform the gravitational field away, and also because of the nonlinear character of GR, the splitting into a background and a wave is problematic. Therefore, here we restrict ourselves to a limit where these general problems are not seen or not directly seen, and these are weak gravitational waves. And this is also what is sufficient for discussing the experimental situation, because the waves that we measure here on Earth, they are extremely weak. They are much weaker than one would naively expect. They come from astrophysical sources. So what we do here is we have weak gravitational waves where we actually can split the solutions into the background, which is maybe flat typically, and the wave. And the problems in the full theory we will only briefly touch. Now we can divide up this chapter into 3 parts: the propagation of the waves, the emission, and the detection. So the propagation is, of course, what happens then in the empty space, but the emission is then needed to understand the generation of the waves. With the detection, I'm rather brief because this is more an experimental topic. I only give you the things of principle. Now, let us start with the propagation of the gravitational waves, and let me recall first the linear approximation that we had earlier. Linear approximation. So we did that in section 6.2, and it consists in the following. We can write a space-time metric g mu nu of x into 2 parts: the background, which we choose here to be flat, and a constant eta mu nu, and a small deviation called 2 psi mu nu of x. And we neglect higher order terms which are quadratic in this and quadratic in the derivatives and so on. So that's the assumption that underlies what we do in the chapter 7. And of course we use adapted coordinates, which are the inertial coordinates related with eta mu nu, which means that this here is not a general tensor. It's only a tensor with respect to the restricted, what we call the gauge transformation of linearized gravity. Index motion is done with the eta mu nu, so there's no problem even if you have partial derivative to raise and lower indices here. We have seen in that section that in how to derive the linearized Einstein equations, and we have seen that we can do this in a simplified way if you choose a so-called gauge condition, and this gauge condition is called the harmonic condition or the Donder condition. So if we assume that psi mu nu, nu is 1/2 the derivative of the trace. So this is the harmonic condition. Then, similarly to using the Lorentz gauge in electrodynamics, we can decouple the various components of psi mu nu and have an autonomous equation for that. And these are the linearized Einstein equations. So we have D'Alembert psi mu rho is minus kappa T mu rho minus 1/2 eta mu rho times the trace of the energy momentum tensor. Yeah, so this has a similar structure to the wave equation in electrodynamics. So it has the structure that D'Alembert of psi is equal to the source. We can still simplify this somewhat. You see here on the right hand side we have not just T mu nu but this combination, and we can get rid of this by redefining the psi. Of course we are free to do that, so we define now a new field phi mu rho. That's just a redefinition of the psi, and so it's psi mu rho minus 1/2 eta mu rho, and you have the trace here. So using this harmonic condition for psi, I think you already see it by looking at this. We find that this translates into the following condition for phi, right? So there it looks really similar to a Lorentz condition in electrodynamics here, and we call it also the harmonic condition here. Also we can simplify the wave equation, and you can easily check that in that you just replace here the psi by the phi here, and so you will see that from here we get an D'Alembert of phi mu rho is minus kappa T mu rho. Well, that was the purpose of this redefinition. Yeah, so we have here then the simple form of the linearized Einstein equation. So you see really directly D'Alembert phi mu rho is proportional to the energy momentum tensor, and that's the direct analog to what you know from electrodynamics. So this corresponds to D'Alembert A mu is minus 4 pi j u. Not that. So you see this is a one-to-one analogy. Of course with an important difference, because these are tensors and these are vectors. So we have to take the freedom into account that these tensor fields have. Now we already did that. We have in section 6.2 checked, how or calculate how the psi transforms when you go to a new coordinate system. So in section 6.2 we have seen that we go then to a psi prime. Psi mu nu prime of x prime is psi mu nu of x plus f mu comma nu of x plus f nu comma mu of x under x mu is x prime mu plus 2f mu of x prime. So if you do an infinitesimal coordinate transformation, we have seen in that section that the psi has this transformation, this inhomogeneous transformation, similar to the A in electrodynamics, so the original one plus these two gradients. Now, of course, you can also do that for phi. You just use this formula and insert that, and so from here you get that phi mu nu prime of x prime is phi mu nu of x, and then you get also, of course, f terms, but because of this redefinition you get here another term minus eta mu nu f rho comma rho of sx. Now, of course, we must demand that also the transformed phi, which is the phi prime, obey the harmonic gauge condition. So phi mu nu prime of comma nu is 0, like this. I mean, we also want to have this, so we should, to keep the form of this equation, of course, we should stay inside the class of functions with that. And of course, the question is, what freedom do we have concerning the f? Certainly, if you make a general transformation with a general f, you run outside this harmonic gauge condition. So you have to check. No? You have to insert this here and demand the vanishing of this divergence. And what you actually get from this is a restriction on f. And I don't do the calculation. It's simple. You just insert that, and you find that you must demand that D'Alembert of f vanishes. So this still leaves you a lot of freedom, because the free wave equation, the free D'Alembert equation, has many solutions, as you know from your elementary classes. So which means that you have many solutions which leave the harmonic condition untouched, and we will make use of that to simplify things further later. So in this section 7.1, as I said, we first discussed the propagation, and we go to the emission later. So propagation means we neglect here the right hand side. The waves have somehow been generated, and now we study their propagation in empty space. So for the propagation of the waves, we set T nu equal to 0. So we have D'Alembert f mu nu is 0. And this, of course, holds also for the original psi mu nu, because here that difference here on the right side does not matter. So we have here the free wave equation for those tensor fields, and certainly we cannot simplify this further. Let me recall, I mean, this D'Alembert is the free D'Alembert operator, which is minus, if I take into account the speed of light, minus 1 over c squared, d squared over dt squared, plus nabla squared. No, so that's what we have to use, in contrast to the full covariant D'Alembert operator with respect to the full metric, which is not needed here. So you see, because here we have the speed of light, and this is a standard wave equation, you see that the gravitational, well, we have not yet seen these are waves, but these gravitational actions that they propagate with the speed of light, as electromagnetic waves do. I mean, strictly speaking, this is a heuristic argument only because we need to check this for the energy transport. I mean, these are coordinate-dependent quantities, so it could be a coordinate artifact, but it turns out it is not. When we discuss the energy transport, I mean, I will say that. And also one should formulate this with invariant quantities like curvatures and so on. But this is what holds, and so what you see here at that level is also true for the precise formulation. No? So gravitational waves, at least heuristically, we see from this, the wave solutions, we call solutions of these gravitational waves, propagate with the speed of light, as electromagnetic waves do. Now let us be a bit more specific and consider a wave propagating in positive x direction. So consider a wave propagating in positive x direction. Okay, this is just a choice, it has no intrinsic meaning. We again set speed of light equal to 1, and so we make the ansatz phi mu nu on depending on t minus x. And you know that this is a solution to the wave equation here, and it describes a wave propagating in the one spatial direction, which is here chosen to be the x direction. Now, we want, of course, to solve the wave equation, but we also want to exploit the harmonic condition to make life simple. And you will see at what simple expression we arrive. So we use phi mu nu comma nu equals 0. Okay, if I write this out, then I get phi mu 0 comma 0 plus phi mu 1 comma 1, yeah, with respect to t and with respect to x, and there's no other dependence. So the derivative with respect to, well, I should have written it better in that form, 0, 0 and 1, 1, so that I can use here phi mu 0 dot. No, so the comma 0 downstairs gives you the dot, and this is of course the derivative with respect to x of phi mu 1, and of course you see, because this depends on t minus x, the derivative with respect to x is minus the derivative with respect to t. So this here is minus d over dt phi mu 1, which we call a minus phi mu 1, or which is minus phi mu 1 dot. So that this is phi mu 0 dot minus phi mu 1 dot, and of course this must be 0, so this is 0. Now you see here, this you can directly solve. It means that phi mu 0 minus phi mu 1 is a constant, but this constant is irrelevant. So let us, okay, from this let us first choose the time components. So mu equals 0, so we get then from this that phi 0 0 is equal to phi 0 1. Yeah, the constant is negligible. Okay, this here we can move the indices with eta, so this is phi 0 1. This is symmetric, so this is phi 1 0, and so we can raise the 0, but this gives a minus sign. So this is minus phi 1 0, and then if you use here from this the component mu equals 1, then of course you get here minus phi 1 1. This means that phi 1 0 is phi 1 1. Okay, so we have this here, and also we can relate it to that, and similarly you can do this for the other components. So we can also have then phi 2 0 is the same as phi 2 1, and phi 3 0 is phi 3 1. No? So you see, I mean, this here, of course, because mu goes from 0 to 3, these are 4 equations, and so 4 conditions that restrict you to 4 less components. So we have here 1, 2, 3, 4 restrictions on the phi. So this means that phi mu nu has no longer 10 independent components as you expect for a symmetric matrix, but 10 minus 4, which is 6 components. No? So we have 4 conditions, and so phi mu nu now has 10 minus 4, which is 6 independent components, by using the harmonic condition. But as we have argued here, you have more freedom. Yeah, you can make this transformation, and if this is obeyed, we remain in the harmonic gauge. So let us exploit that. So let us make such a transformation and choose the f's such that they, of course, obey that, but that they restrict further the amount of independent components. And because these are 4 f's mu, 4 further conditions will reduce this to 6 minus 4, which are 2 independent components for phi. So let us use the remaining coordinate transformations, which is x mu goes to x prime mu which is x mu minus 2 f mu with D'Alembert f mu is 0. And of course, any function f mu that depends only on t minus x is a solution of that. So this is in accordance with the ansatz phi mu nu depends on t minus x. So whatever you use which depends here on t minus x, obeys that, and you can use. So so use this, use them to eliminate 4 additional components from phi mu nu, and so you are left. So we are left with 10 minus 4 minus 4, which are 2 independent components for phi, for the solution. So that we cannot reduce further. Now, how does this work in detail? Let me only sketch that. I mean, we have this transformation, phi prime is phi plus f comma nu minus this term, and this we shall use. For example, let us use here 2 0. Then we have here, I mean, 2 0, or I write it for your convenience here, that you directly see how it works. So we have this here. Yeah, and so in particular, if we have here 2 phi 2 0 prime, so you have phi 2 0, and then you have phi 2 dot, the only term, right? Because here this is the temporal derivative, but there's no derivative with respect to the 2 direction, which is the y direction. Also eta 2 0, because eta is diagonal, is 0. So from this we can choose, I mean, f2 dot is a minus phi 2 dot. I mean, we are free to choose our f as we want, and so we can achieve that phi 2 0 prime is 0. No? So we use this remaining freedom to simplify as much as we can, and you see, for example, the transformed phi to 0, we can choose 0, and we can do the same for phi 3 0. By the same argument, 2 and 3 are symmetric. Now for phi 1 0, of course, you have to take into account this additional term. So this is phi 1 0 plus f1 dot plus df 0 over dx, which is phi 1 0 plus f1 dot minus f0 dot. And to achieve here that this vanish, of course, we can choose here this difference. So we can here choose also phi 0 1 prime is equal to 0. Not just by demanding that this here is minus phi 1 0. Finally, let us investigate a trace of phi mu nu prime. So phi prime mu is phi mu plus 2 f mu comma mu minus 4 f mu comma mu, and so this is then phi mu minus 2 f mu comma mu. And if I expand this, so then I mean this latter one, so this is of course the original trace, and then we have 2 f0 dot. I mean, here you have a change of sign because f0 comma 0 upstairs is a minus f0 comma 0 downstairs, but with the downstairs we have defined a dot, and so we have minus 2f minus 2 df over df1 over dx, which is minus f1 dot. So we have that this is phi mu mu plus 2 f0 dot plus f1 dot. And so you see here we have, this is why I did that. I mean, here we have a condition then on the difference, and here we then have a condition on the sum. And this is why we can do this independently. So we can choose the transform trace to 0 by setting this to minus f phi mu mu. So we choose f0 plus f1 dot is a minus 1/2 phi mu comma mu. And so we have here phi prime mu comma mu is equal to 0. Okay, this means that also the transform trace of the original one is 0, because if you have, you see here, this is the redefinition. So if this trace is 0, then also the trace of this is 0 if you perform the trace. And all in all, you can choose here then phi mu nu prime is equal to psi mu nu prime, if you collect this together. So in the following, for simplicity, we skip the primes. So we have done that job and gone to that coordinate system where we have only 2 degrees of freedom left, which are the psi 2, 2 and the psi 2, 3. And let me just write down now the result. So to summarize, we have arrived at the following form of the perturbed metric. In our case, where it depends only on t minus x. And if I write this as a matrix, as a 4 times 4 matrix, it has the following form. So we have seen that those components here are 0, and also these components here, and that we only have non-vanishing components in this 2 cos times 2 subset, and we can write it as 2 psi 2, 2, psi 2, 3. It's symmetric, so it's the same psi 2, 3, and the trace is 0, so we can write minus psi 2, 2. No? So you see, we have simplified our problem drastically. So we just have 2 remaining components that by convention we wrote in this form. So we have only 2 degrees of freedom. So 2 degrees, so only 2 degrees of freedom. And so we have now fully fixed the gauge, or in other words, we have made maximal use of our coordinate freedom at a linearized level. Now, we had a harmonic gauge, which are 4 conditions, and this left us the remaining freedom of 4 coordinate transformations in that restricted class, and this left us 2 degrees of freedom. And this gauge, I mean this fixation of coordinates, has a certain name, and it's called the transverse traceless, or TT, standing for transverse traceless gauge. And this is what is usually assumed in this context. So most of the time, by giving certain expressions, we are in this TT gauge. This is what you should remember. I also want to write down the line element, and of course this you can directly then take from this. So recall we had G mu nu is eta mu nu plus 2 psi mu nu. And the line element is G mu nu dx nu. So the line element reads then as follows, that ds squared is then minus dt squared plus dx squared, because you have in the xt direction there's no change. So this is just from the eta, but we have of course differences here. So we have here plus 1 plus 2 psi dy squared plus 1 minus 2 psi z squared, and then we have also a non-diagonal term, so 2 times this and 2 times this, so we get 4 times psi to 3 dy dz. Now, so that is then the desired or the looked for form of the line element of the geometry. No, so you see here we just have here modifications, and also here, and we shall see next time, I mean, how to interpret them. What do they mean? I should just say in passing, and this can be shown easily, but I will not write it down, that the combination psi to 2 minus psi 3, 3, I mean, if you have a general psi 3, 3, not, I mean, here it's just here psi to 2, that this is gauge invariant. So it's not changed by a coordinate transformation. Yeah, so of course this is here equal to twice psi to 2 in the t gauge. But even if you went beyond, then this would be gauge invariant, and one also has psi 5 to 2 minus phi 3, 3 is the same as psi to 2 minus psi 3, 3, because the trace term cancels out. So for appropriate initial conditions, you could choose the 2 psi 2, 3, which is also gauge invariant, as it turned out its derivative, and this combination and its derivative. But we stay here in the TT gauge where we have this particular form. Now, so far for the solution, in the following we have to study its meaning, and the first is of course to investigate generally the behavior of test particles in the field of gravitational waves. Because this is pure geometry, so if that wave comes and there's a test particle, which means has no further forces, so these test particles will experience this geometry, so by measuring space-time distances. So let us start with that. This will also be relevant then for the detection, because this will be the principal feature for the detection. So let us investigate the behavior of test particles in the field of a gravitational wave. Now, test particles move on geodesics. So test particles move on geodesics. So we have to study the geodesic equation of motion, which you know is the second derivative with respect to proper time, and then you have this term with the Christoffel and the first derivative. And these first derivatives, of course, are our 4 velocities. Now let us assume we have a small perturbation, of course, from a small wave amplitude. We take into account then also only the first order in delta x mu delta x. So we have a small perturbation of the coordinates of these test particles, delta x mu. So then we get from this equation here that d squared of delta x mu of the s squared is a minus then the perturbed gamma and u mu u lambda. So this is the first order perturbation in the gamma. I mean, the propagation is here in the background of Minkowski space-time, and if you use inertial coordinates, the gamma of the background are 0. So we only have here of course, the perturbation. Now you might ask why we don't have now a term maybe where you have the gamma times delta u, or here this delta u, but again the argument is that the gamma of the background is 0, so it does not contribute. The only contribution is here. So if we assume that the particles are initially at rest, particles initially at rest, we shall see later that we typically start from just from a circular distribution of dust particles at rest. So we have here the initial value of the forward velocity has only a temporal component, because the spatial component is a spatial velocity and this is 0. And if we insert that, then you get from this here that d squared delta x mu over the s squared is approximately then minus gamma delta gamma mu 0, 0, because this here we sum over nu and lambda, but only the temporal component contributes. So we have to know what this is, and so I refer again to section 6.2 of linearized gravity when I gave you the expression of the Christoffel symbols in terms of the psi. And you just have to look this up. So this here is section 6.2 minus psi mu 0, 0 minus psi mu 0, 0 plus psi 0, 0, mu. Now if we insert this into this line element here, then you see that all the psi mu 0, they are 0. So this is just 0, which means that we have here d squared over d x mu over the s squared is approximately 0, which means that if you choose initial condition that the delta initially is 0 and also its first derivative is 0. Otherwise you have some integration constant that delta x mu of 0 is 0. For all s and for all test particles. This means that for first order the test particles are at a fixed coordinate value. So the coordinate values do not change. So to first order the test particles are at a fixed coordinate. Now the emphasis is on coordinate value. And because coordinate value is not yet the physical distance, and the physical distance you have to check from here. But from this you see here that the coordinates, you will see the test particles, they will move, as an effect of the passing wave, but the coordinates will be the same. But the physical distances will change. Let me do this here at the end of today's lecture. Calculate. So what about the physical distances? So if I have here the coordinates, so y and z, so these are the transversal coordinates, so the wave is in x direction here. And if we have here two particles 1 and 2, and we have an initial length L naught, so this is here L naught. So it's a coordinate distance, but if we have flat space time before the wave comes, it's of course also the physical distance. So this is a coordinate distance, which is the same as the physical distance in flat space time. Now, what happens now with the physical distance if the wave impinges on this yz plane? So physical distance if wave pinches on the YZ plane, no, then you have an L of them depends on t, and of course then you have to get this from here. Yeah, so if we consider the length along the y-axis only, then of course the dz is 0, and we just have to consider the dy part, no? Because this is 0 and this is 0. So then we have L of t is then the integral from 0 to L0 dy, no? So the fixed coordinate distance. And then we have from the line element square root of 1 plus 2 psi to 2 of t and 0. No? So we evaluate this at x equals 0 because this is the zy plane where x is 0. Now, okay, this here is very small, so we can expand the square root and perform the integration. So we have L0 times 1 plus 2 psi to 2 of t and 0. So the difference between the L of t and the original L0 is then L of t minus L0, and if you make this dimensionless, divide by L0, so we call this delta L of t over L0. Then you see here, no, from this is just the side. Oh, here is a mistake. Now the expansion of the square root gives here 1/2, and so we have here psi to 2 of t and 0. So you see here that this psi to 2 then directly gives you the change of the physical distance. So for example, if you have a wave with psi to 2 of t and x is, let me call it a over 2, the sine of omega t minus x plus phi, and also a sinusoidal wave. I write here a over 2 because the 2 psi is the real amplitude, because this is in the metric perturbation. So then we get the delta L of t over L0 is approximately a over 2 sine omega t plus phi. So you see that the distance between the particles, say in this case between particle 1 and 2, oscillates with the wave. So the wave comes with a frequency, angular frequency omega, in the form sine of omega t plus phi, and the physical distance oscillates. So we have the result that the distance between the particles oscillates with the frequency of the wave. So if a wave comes from somewhere, then you could measure in principle the amplitude of that wave and its frequency by just looking at test particles. Now we shall see that unfortunately this amplitude is very small. So in a realistic situation, A is typically of the order 10 to the minus 21, say, as one number. I mean, there will be a range, but in realistic situations. So you need a lot of experimental effort and cleverness to measure this. But after decades of attempts, this was really successful a couple of years ago. And we shall discuss this. Now let me finally write down, I mean, from this line element, I mean, the distance between two neighboring particles, so the spatial distance, so t is constant. So we have the spatial line element, and the distance is then given by the square root. So the distance between two neighboring particles is then, I call it the sigma. The spatial distance is then the square root of the x squared plus 1 plus 2 psi psi dy squared plus 1 minus 2 psi psi dz squared plus 4 psi 2 3 dy dz, not a square root. So you see here, I mean, as you already saw before, that the distances in x directions remain unchanged. So you see only the direction orthogonal to the propagation. The propagation this direction, and the distance is only orthogonal to its change, which is here, or you could also have two particles here. And so this we call a transversal polarization of the wave. Now the effects are only transversal to the direction of propagation, as you know from electromagnetic waves. So here you see distances parallel to the x-axis remain unchanged. And so we call this a transversal polarization. So, so far for today. Next time we start from this and discuss in detail the behavior of a ring of test particles under the passing of a gravitational waves. And this will be done by first discussing two subcases, namely the one where you only have psi 2 non-vanishing, and then where you only have psi 2 vanishing. This will give us two linearly independent polarization states, which we can add up and also form, as in electrodynamics, circular and elliptical polarizations. Thank you for listening today, and hope that you stay tuned also for the following section. Bye.